Principle of superposition states that the total displacement or internal force at a point in a structure under multiple loads is equal to the sum of the effects from each load acting individually. But for superposition to be valid, two conditions must be met. First, the material must behave in a linear elastic manner. Secondly, there must not be any significant change in the geometry of the structure under load. To solve for internal displacement, we use the equations of equilibrium, where the sum of forces in x direction is equal to 0, sum of forces in y direction is equal to 0, and sum of moments about a point is equal to 0. But before we apply these equations, we need to ensure that structure is both statically determinate and stable. A structure is statically determinate if the number of unknown reactions is equal to number of equations, or in other words, R is equal to 3n. If there are more unknown reaction forces than the equations, then a structure is statically indeterminate, and mathematically it could be said R is greater than 3n, where R is our reaction forces and n is a number of equations. Next, we must assess if a structure is geometrically stable. So in this case, a structure could be unstable if it is partially constrained. For example, here in this example, this structure has proper restraint in y directions, but there aren't any constraints that are preventing it from going left or right or in any direction of the axis. The second scenario is where a structure is improperly constrained. In this case, or in some cases, you can say there are as many unknown reaction forces as there are equations of equilibrium. However, there is instability in the structure because of improper constraining by the support. Here we can see that this structure is properly constrained for forces in y direction, but there isn't any constraint in the x-axis. Classify each of the structures as statically determinate, statically indeterminate, or unstable. To solve these, first of all, we need to draw our free body diagram. For this structure, we know that on the leftmost section we'll have reaction force in y direction and reaction force in x direction, and in the center we'll have just one force in y direction. So here we can see that we have three reactions, and we know that we only have one segment. Therefore, we have 3 equals to 3. That means our structure is determinate, statically determinate. And then now for a second, if we draw our free body diagram for this one, for leftmost part, we know that it will be similar to first. We'll have forces in x and y direction, but we'll also have moment here because of the law, and then we'll have 2 forces in y direction in the center. So for this particular problem, we have 5 reactions in total, and we have 1 segment. Therefore, we have imbalance where our reaction forces are greater than our number of equations, and this makes this as indeterminate. And finally, for our last one, we can divide this into 2 chunks and solve it. So for first portion, we know there will be 1 force in the x direction, and there will be a moment here. And for the other side of this component, there will be x and y forces. The same thing on the other side for the other segment, there will be x and y component, and then again for x and y component. So for this, these are just just 2 reactions, just being on opposite end. And then we have 2 reactions here and 2 reactions here. In total, we have 6 reactions, and we have 2 segments. So this is our statically determinate structure. Determine the reactions on the beam in figure. Assume A is a pin and the support at B is a roller. Let's start by drawing our free body diagram. we have 2 points, A and B. We have a distributed load, that's 500 pounds, and we know it's 7 feet long. So times that with our point load, with our distributed load, we get a point load of 3,500 pounds. And this is halfway through, that means it's 3.5 feet away from point A. At point A, we have two support reactions. Two reactions, one is in X direction, another one is in Y direction. And we have a reaction at point B, we'll name it FB. And we know that looking at our figure, we're going to have a slope of 3 by 4 at F sub B force. And using the Pythagoras theorem, we know that our hypotenuse will be 5. Now let's take our moment along A. We're going to assume our counterclockwise as our positive moment. So our first point load is 3,500, which is in negative direction. Then our next moment is for our reactions at B in both x-axis and y-axis. For y-axis, it will be 3/5 times our force times our distance from A to B, and this comes up to 10 feet. And then for our x-axis, we have 4/5 times our force times our distance from A to B. That comes up to 4 feet, equals to 0. Solving this, so 3,500 times 0.35 comes up to 12,250. And solving our forces here, so 4 times 4 is 16, and then 30. So 30 and 16 is 46. 46 divided by 5. This comes up to 9.2, and when it goes over to the other side of the equation, it gets divided with our point load for our distributed load. And solving this comes up to 1,331.5 pounds. Now that we have this, we just simply need to find our reactions at A. So we can simply sum our forces in X direction, and we can assume left to right as our positive for the force. So for our FAX, this is going to be positive because it's going left to right, and then our force BX will be negative because it's going the opposite way. So and this would become 4/5 times our force FB, that is we just found. Solving this, we should get really good number here. And this comes up to 1,065.2 pounds. And now for our force in the Y direction, going up would be our positive. FAY would become our positive, and we can see that our FBY will also be positive. But to do that, we need to use our slope times our force we just found. And this would be 3 divided by 5, 798.9. I don't know if you have noticed, but I did miss one force here. That is our point load, 3,500. This is going downwards, so that means this would be subtracting. So that means we need to add our force here, so 3,500 pounds. So when we do that, we get a new value here. So that would be 2,701.1 pounds as our answer. Determine the horizontal and vertical components of reaction at the points A, B, and C of the two-member frame shown in figure. Solve this. Let's first of all draw our free body diagram. And we can use method of section to divide this structure into two components so they are easier to solve. We're going to do it A, B, C. For our point A, we're going to have two reactions, FA in the X direction and in the Y direction. You're going to have similar type of reactions for the point B. Here we have to make sure that whatever the direction our reactions are having in the member AB for point B should be opposite in the member BC. Otherwise, you're gonna have very, very bad values that are not even close to what this structure would experience. Okay, and we can have similarly, two reactions for C as well. And we also have a distributed load of 3 kilonewtons, and it's distributed over 2 meters. And solving this, we would get a point load of 6 kilonewtons for that area, and this point load would be a meter away from point C. Now let's take a moment about point C. I'm going to assume counterclockwise as our positive for every moment equation we're going to do from here onwards. And using this, the first load is 6 kilonewtons, and it's positive, and it's 1 meters away from point C. And then our point FPY is in the opposite direction of our positive, our assumed positive value for our moment. So it's going to be negative, and it's 2 meters away, equals to 0. Solving for this FPY, we get positive 3 kilonewtons. Now let's take a moment about point A. The reason being, we already have a value of Py, we can find the value of Fpx, and that would make our life so much easier in solving this problem. We can do the other way as well. We can find the value of Fcy before doing anything, but we can do that later as well. So we're going to leave that for later. Okay, so now moment at A. Oh, and I forgot, there is a point located for 8 kilonewtons. Okay, so we encounter our point 8 kilonewton point load, and it's in negative direction because it's clockwise, and it's 2 meters away from our point. Then we have our negative force By, and we already have the value, that's 3 kilonewtons, and this force is 2 meters away from our point, and then we have negative Fpx, and this is 0.5 meters away from our point. Okay, so now solving for force Px, so that's 16 plus 6, that's 22, so 22 divided by 0.5 comes up to 14.67 kilonewton. Okay, so now we also need to remember about our sign. So these would become positive on the other side, and this negative stays, so it'll be negative. It'll be negative 14.67. Don't worry about it. I'll show you why it is negative and how it's going to become positive later on in this problem. Okay, so now that we have that value, we can find the value of r along the x-axis. So let's do sum of x-axis at member AB. We can assume left to right as our positive. So our FAY would be positive. Then our point load 8 kilonewton will be positive. And we're going to have a negative 14.67 kilonewton as our kilonewton equals to 0. Solving this, we get 8 times 3 is 24 divided by 5, 14.67, and we get 9.87 kilonewton as our value for Fx. Okay, Fx. Okay, so we have found the value of Fx. We have found the value of Fpx. What else is remaining? Okay, so we are missing Fay. Okay, so let's do sum of forces along y-axis, and that should give us our Fay. And we can assume going up as our positive. So we have Fay, we have negative 4 over 5 times 8 for point load, and then we have found our value for Fpy, and we have a negative, so it's going down, so negative, and then we have 3 kilonewtons, so 0. So in solving for Fay, we get 4 times 8 divided by 5 and plus 3 comes up to 9.4 kilonewton positive. Okay, and now let's do real quick our values for point C. So sum of forces in the x direction at member BC. So at member BC, we know our Fpx was, its Fpx is negative, and Fpx is negative and negative, because we have one negative here, because of the out of the direction, and then we have a negative from our value, negative 14.67 kilonewton. Okay, and then we have our positive force Cx equals to 0. And force Cx is equal to negative 14.67 kilonewton. And then we're going to do same thing, sum of forces along y-axis for member BC. So we know that our FBY is positive 3 kilonewton. And then we have negative 6 kilonewton for our point load. That was distributed load. And then we have negative FCY equals to 0. Solving for this, our FCY, so negative 6 taken with 3, so negative 3 becomes positive 3 and becomes negative 3 kilonewtons. Okay, alright, so now this is where we can correct our signs. So you see, wherever we have a negative value, that means we assume the wrong direction for our arrow. So that means our value for FCY, first of all, because it's negative 3 kilonewton, if we flip this sign to up, we can change this to positive. So now that value is positive. Our FCX has similar issues, so we made it positive. We can flip our sign the other way. Okay, alright, so and then what else do we have as a negative? Our PX. Our force PX, well, it doesn't really matter because this, once the structure is joined, it doesn't matter, it cancels each other out. Okay, and we know that these two are correct now because they are balancing each other out, and we know that this makes our structure stable. Like and subscribe for more.